Okay, so let's get started. So the plan for today is continue with the neural network lecture. And then after that, if we have time, and that's the kind of plan, to get to the probabilistic models. So just a very quick, I go through it very quickly. So we talked about neural networks. They are inspired by the brain, but they are not exactly how a brain works. So we just try to kind of imitate the how some, say, for example, a neuron in the brain works by having a simple model like this that's saying that a neuron takes some inputs and then computes some, multiplied with some weights, and then generate some outputs. And usually we do this through saying that we have this W transpose X plus B, and then after that it goes through some activation function, and that would be the output of that neuron. And then we have different activation functions. For example, it can be a hard threshold, it can be a ReLU, it can be a hyperbolic tangent, or things like that. So the thing about the type of neural network that we talk about is that we put many of these units, neurons, in a feed-forward way. So we put them in a directly cyclic graph structure, and usually we put them in some form of layers. So we have an input layer. Its input, the input layer goes to some first hidden layer. Some processing is done there, some multiplication by weights, and then going through some activation function. The output of the first hidden layer goes to the second one, and so on and so forth, until it gets to the output layer. So I mentioned activation function, for example, it can be identity, rectified linear unit, or ReLU, stuffed ReLU, or, for example, it can be hard threshold, or hyperbolic tangent, and many others. So there are a lot of activation functions. And then the structure, as I mentioned, can be put in in what is called feed-forward neural network or multi-layer perceptron. They are put in this linear structure that, as I mentioned, input goes multiplied by W1, which is a matrix. It goes through activation function, and then it generates H1. And then H1 goes here, multiplied by the weight in the second layer, and so on until we get to the last layer. So I guess that was an exercise, and I think this was the last place I talked about. Okay, so what I was talking, so the last thing I think I was talking about is that, well, what should we do for activation function of last layer? Usually the way we choose it, if the task that we want to solve is a regression task, we just choose a linear activation function. So essentially, we just multiply the weights by the output of the hidden layer, maybe add some bias, and then that would be our output of our network. But then if the task is, for example, a classification task, then we pass it through some form of logistic function, which basically makes sure that the output is between, say, 0 and 1, so that the interpretation of the output of that neural network would be some probability of, for example, class being 1. And if it is multi-classification problem, it would be softmax instead of that. So if you recall, one thing that I think even was the start of this lecture was the question of how we choose our models, what kind of models we can have. So maybe I'll just go back through it as a quick reminder that, okay, so we have this model, the input goes into it, generates some output. So far, most of the work that we had done was based on this idea that we take some linear model, essentially, and then that would be the model that relates the input to output. But then we noticed that this is quite limiting. So what we did was in adding some kind of features here, phi. So phi transpose W, that would be the output of that our model. So this is still a linear model, but not linear in inputs anymore. So it is more capable. And also in the discussion of kernel-based methods, in the context of, say, support vector machines, we talked about the idea of kernel that allows us to do this computation without actually computing this phi. But in any case, in all these cases, we had to choose phi or the kernel that is defined based on phis ourselves. So that is a kind of limitation of these previous methods that we worked with, because someone had to choose this phi. One of the motivation for neural networks is to try to learn these features, these phis, in an automatic way, instead of specifying it. And we can see that essentially a neural network, this structure, we can think of it like this, that the input goes to a bunch of layers, and in the last layer, it becomes some function phi of x. And phi of x is effectively basically some processing on the input based on the weights of all the previous layers. So what happens then afterward? We take, for example, in this case of regression, you see that this output, which is the last hidden layer, the output of last hidden layer, is phi of x. It is multiplied by some w, and that would be our output of our neural network. Or it would be the same, a linear combination plus some nonlinearity, for example, a logistic function to make it a probabilistic interpretation. So you see that effectively a neural network is giving us this phi of x. And by learning a neural network, or the weights of a neural network, which I'm going to talk about later, we can learn this feature mapping. So this is the kind of important thing about neural networks, and one of the very desirable things about them, that they basically, we don't need to specify the feature mapping anymore, but it learns it itself. And if it is assuming, if it's successful learning it, that is a kind of very desirable thing. Okay, so just give you an example of how these features might look like. We can look at different output of different layers and see what kind of processing it is doing. So, for example, trying to assume that, or suppose that you are trying to classify images of handwritten digits. So each image is represented by kind of 28 by 28 matrix, or we can see it as a vector, 784 pixel vector. Then if we learn a neural network, and we see how we can do it, and then just take one of the units in the first layer, the first hidden layer, it is effectively computing something like this, that some Wi transpose x through some mappings, so through some phi. So this would be the output of that neural network, and this acts, you can interpret it as some kind of feature detector. Feature in this case means features of the images. And then we can visualize what kind of behavior it is doing by just seeing, after learning, look at the W's and convert it to an image-like form, like 28 by 28 like image, and then see how it looks like. And if we do it, for example, one of the weights would look like this. So what does it do? I mean, it might be a bit difficult to say, but okay, so like here, basically brighter points are, for example, the larger weights, negative would be negative weights. So it looks like it is kind of maybe. So kind of paying attention to this part of the image. So it seems that it is looking at maybe some aspect of the pixel of the kind of digit that has this kind of diagonal shape. So why? Because you see that those are the larger weights. So when you multiply that larger weight by the input, it becomes more sensitive to those specific pixels, which has a larger weight in magnitude. And if we look at many other weights, we see that they have this type of patterns that, say, for example, each of them looking at, like, paying attention here, 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 maybe here. So these are the negative values, which kind of suggests that each of these units are paying attention to one particular part of the image and kind of extracting information from that part. So these images, if you look, it's not quite obvious that, well, this is detecting in pixel digit 5, for example. But you can see that it is looking at part of maybe pixel digit 5 or another digit. And then the next layers essentially would try to combine the activation of each of them, which each of them, for example, paying attention to diagonal structure or, for example, horizontal structure, and by combining them, trying to make a decision.
I have a question.
Sure. Yeah, just a second. Yes.
Yeah. So, what are these images? Are these the output of hidden layer, or they are the weights?
These are the weights.
The weights. Okay.
So these are the weights. So essentially, so these are exactly these W's. And if the weight is large in magnitude, it means that it's more sensitive or paying more attention to that, the corresponding X or pixel in that input X.
This weight is a matrix. Why is it like two-dimensional?
So this is the whole weight of, yeah, that's a good point. The whole weight of that layer is a matrix, but we can look at weights of one unit, the weights that is connected from input to one of the units, and that would be a vector.
Yeah, okay.
So if you see more, I'm not going to talk about it much, but like if some more kind of larger neural networks, if you have multiple layers and they are detecting images, for example, more complex than digit, you would see structure in the weights that they are learning. Or there are other techniques to also figure out what each unit is trying to kind of reacting most to it. So it is not exactly weight, but trying to figure out which, what is the most exciting input for that specific unit. So what we see is usually that in the first few layers, first one or two layers, it is starting to detect basic structures of the image. For example, horizontal lines or vertical lines. Essentially, it acts like some form of edge detector. But then as you go further in the network, you will see that they are more sensitive to things like maybe part of a body. So if the input is an animal or humans, so they become, for example, sensitive to eyes or nose. And then gradually, basically, what they are kind of capturing is, for example, where is the nose? And then having these type of features that would be very difficult to manually design would help these neural networks to pay attention, to do kind of a very good job in, say, classification. Okay, so one thing that you probably remember is that there are some functions that cannot be represented, or some classes that cannot be discriminated by a linear classifier. So a simple example was an XOR case that you cannot use a linear classifier to separate them. And we had to use, for example, some form of nonlinearity. So one question is that, okay, so are deep neural networks, or neural networks generally, are better or not? So just start with a simple case that suppose we have a neural network, multiple layer, but each layer's activation function is just the identity function. So we take input, do some multiplication. Each layer takes an input, multiplied by some weight, and then the output of it would be just exactly the output of multiplication of that weight. So there is no nonlinearity. So this is a linear layer, and the result of them, if we put them, would be basically like this. So we have that X multiplied by W1, W2, W3, and say so on and so forth. So this, a neural network with linear layers, if all of them are linear, can essentially be equivalently represented with a single linear layer. How? We just take all these weights, W1, W2, W3, that's a matrix again. So that would be W prime. So the network essentially is doing a multilinear computation on the input. So deep linear neural networks are not more expressive than linear model. Maybe this would be, I don't want to focus on linear regression. But then if we add some nonlinearity in the activations, then they can become much more powerful. So under some conditions, they are, with many nonlinearities, they become universal function approximators. What does it mean? Universal means that they can approximate any function, any reasonable function, arbitrarily well. So for example, if any continuous function, you can always find a neural network with certain architecture that can be epsilon close to that function and close in some specific sense that can be defined. So there are different ways to define it, but the point is that they can be very close and approximate that function very well. And this has been shown for various activation functions like thresholds, logistics, ReLU, and many others. Yes?
So this is if we use the same nonlinearity,
so even, I guess it would be the same nonlinearity, at least in the hidden layer. I mean, the output layer probably should be linear so that it can represent all range of it.
But in the hidden one, it's always the same.
Yes. Yes, all units would be the same. And actually, these results show that, for example, it is enough to have one or two hidden layers to represent it. So you don't need to have a very deep neural network to represent arbitrary function. The catch is the number of units that you need to have can be very large. So essentially, it can be these results are in the form of, if you have infinite number of units or number of units going to infinity, your hidden layer, that's enough to represent arbitrary function. But this is not exactly what we want. And I'm getting back to this soon. So, and this is even true for ReLU, which is almost, part of it is linear. Both parts of it is linear, but there is a nonlinearity. So, the whole function activation function is nonlinear.
Excuse me.
So just let's see how, let's start from simple cases that assume that we want to learn, classify XOR. XOR was one of the cases that we can't use a linear model to discriminate, to classify. So here, this is the structure X1 and X2, and then we have hidden layer 1, hidden unit 1 and 2, and these ones here are the bias terms. So we add that bias terms. Now what we want to do is find weights. So essentially, what weight should we have here to each of these units in order to be able to classify XOR. Okay, so what we can compute is that we can look at these each of these hidden units as computing some simple binary manipulation on inputs. So for example, if for each H1, maybe we can think of it like this. Yeah, so let's see how we can make H1 computing X1 or X2. So you see that if the weights, if we have something like this, and we are using hard threshold. So if we compute X1 plus X2 and subtract 0.5 to it, and then essentially have a threshold, check whether it's larger than 0 or not, that would compute 0 for or function for us, right? So for example, if this is 0, 0 minus half, so it would be negative, so it would be 0 the output. If it is 1, 0 minus half, it would be positive, so the output would be 1. And for the other cases. So for H1, we just need to put like 1 here, and half here. For H2, we want to compute OR AND function of them. So AND of X1 and X2, we can do similarly, just X1 plus X2, but with a different threshold for different bias, or weight for the bias. So it would be minus 1.5, and you can verify that it is computing AND. Now suppose we want to compute, and okay, to solve the problem, solve the XOR, we need to compute, we want to compute X1, XOR X2, which can be written as H1 and not of H2, and that would be written as H1 minus H2 minus 0.5. So, and we know how to do it. So this can also be written as H1 plus 1 minus H2, which is clear as a kind of not, minus 1.5, which is used for the AND here. So we again find the weights. After we have output of H1 and H2, we can find the weights that computes XOR. So this kind of suggests you that we essentially can compute any binary combination, any binary function, any function of the inputs using these elements. We can always define a circuit that is consisting of ANDs, ORs, and NOTs in order to generate any binary relation, any binary function. So this is just one example. And we can show that, well, I think I kind of argued that any input, any binary function can be represented by a combination of ANDs, ORs, and NOTs. So I showed you how to make each of them. So we can combine them to make any arbitrary function. There is also, I mean, another way to maybe think about it is that, well, suppose we have hard threshold hidden units and linear outputs, and now we have these inputs, for example, X for X1, X2, X3, for each of the combinations, like -1 or +1, so -1 represents false, for example. This is the desired output. And essentially, this shows that we can do this computation. We can design for each of these possible combinations of input, one unit that generates the desired output, which is +1 here. And we have, in general, we have in total 2 to the power of d different combinations for any function which has d variables. And we can combine them in this way so that each of the hidden units generate the desired output here. And then we can combine them in order to generate the output. Now we'll look at this slide and try to figure out why, for example, these specific weights are chosen in order to generate this value. But this is another strategy that you can always use 2 to the power of d number of units in order to represent any d-dimensional binary function. The catch again, as I mentioned a few minutes ago, is that the number of units that we have become very large. So 2 to the power of d, if d is 3, that's okay. But if d is like 20, 30, that would be many units. So one thing that is kind of important is that you can probably, but not always, but in many cases, you can represent a function in a more compact way, instead of going to 2 to the power of d units by having multiple layers of computation. So instead of having only one unit for each input, maybe you can try to design a circuit that has several layers of computation in order to get more compact results. And there are some theoretical results basically showing that why a deep neural network can be more expressive or compact with the same number of units, total number of units, compared to something which is shallow, which means that only has 1 or 2 hidden layers. So there were some theoretical results for, I think the initial results for the binary functions, Boolean functions, and then gradually it extended to more general functions. Okay, so that was for the threshold function. But the other thing is that suppose we want to use other activation functions. For example, we use logistic activation function. So logistic activation function, the good thing about it is that compared to threshold is that it is differentiable. So we can take derivative, and as you see, having derivative is very important for learning. We saw it before in other contexts. We see it in neural networks soon. But hard threshold didn't have that property. I mean, the derivative is 0 in 2 different regions and doesn't give much information. That's the same. We had that issue for the binary classification. But we can all approximate a hard threshold using a sigmoid function. So this is a sigmoid function. You see that it has this kind of structure that looks like hard threshold. So that would be the hard threshold. And if instead of, say, for example, sigma of x, we compute sigma of 5x, this looks more like a hard threshold. And as you make it larger and larger, it becomes closer to a hard threshold function. So this basically shows that we can approximate a hard threshold by just changing the weights. Okay, so I have some exercises. You can think about it later, but so just to give you kind of some hands-on experience by pen and paper at how a neural network can represent functions, arbitrary functions. So suppose you want to take, you represent a function that takes value of +1 in this region, x between 1 and 2, and 0 elsewhere. So essentially this function that we have. So it's +1 here and 0 elsewhere. Okay? So you want to represent it using a simple neural network with hard threshold activation function. So you want to represent f of x in the form of maybe something like this. That's W1 of phi of x minus B1. So phi is the threshold, hard threshold function, plus W2 phi of x minus B. So here, this is phi is shown here. This is the phi function, so the hard threshold function. So you can represent it in this form. So the question is that what should the W1 and W2 be? And what should be B1 and B2? Can you give me anyone can give me a solution right now? This is not very difficult. So what's W1 and W2?
Excuse me.
W1 is whatever the magnitude of items. And then D2 is 2, and W2 is the negative of whatever that is.
Okay, so the answer was W1 should be 1. The magnitude is
Yeah.
the magnitude is 1 here. So, and B1 would be 1, right?
Yeah.
And W2 would be
-1.
-1, and B2 would be 2, right? So you see that essentially what we are doing here is that we have the kind of compose two functions. One of them looks like this, and the other one looks like the negative of it. But the point that the negative is starting, or different values starting, okay, so maybe I just show the same function at this point. So there is, and then we subtracting them. So W2 acts like a subtractor of it. The choice of B1 or B2 chooses where that threshold, where that change in the function starts. So this is simple, but this kind of suggests that you can represent many functions this way. So for example, if your function was a bit more complex, say, anything. You can, using the same strategy to combine these neurons, units, in order to learn that function. And maybe your function is not that smooth. Maybe your function more looks like okay, so let's say your function is this orange one. So this is a kind of smooth function, but how we can represent it? We can't maybe represent it exactly with these units, but we can approximate it. Like how? So probably you know from something like, okay, so let's maybe just focus on one region. So I can approximate it this way, and then maybe approximate it this way. Approximate it so approximate it this way. So, and you see that as I make these intervals smaller and smaller, I can approximate that function better and better. So this is, with arbitrary precision, I can always find some structure here, some placement. Okay, so maybe another thing is that now when we have this green function, which is like this step-like structure, we can use this hard threshold and proper choice of weights and B biases in order to approximate that function. And then this green function can approximate, not to approximate that orange one, but to exactly represent that orange one. And then the green one, sorry. And then the green function, the green step one can approximate the orange curve arbitrarily well. So this is kind of like the idea that we can represent these functions. So now suppose we don't use threshold, but we use another activation function, for example, ReLU, which looks like this. Now the question is that how we can approximate this function, or represent that function. So in the previous case, we could have an exact representation. In this case, we can only have approximate representation. So approximation looks like W1, W2, and each of them you see that there is a V1, V2 here. Previously, V was the factor that's multiplied. The input was 1, but here you should choose something else. And there are more than 2 terms. Think about it. It shouldn't be very difficult, but that would be kind of nice exercise. So this basically shows that neural networks, or suggests that neural networks are universal. For binary case, it's easy to see. For the general continuous functions, like the inputs are from some d-dimensional Euclidean space, I kind of suggested that how you can make it for one-dimensional case, but of course I didn't prove it. The problem with it is that, well, first of all, you usually need a very large network, exponentially large, exponentially in the size of the dimension of the input. Then the other, so that's one issue. And usually we can have a much smaller network if we go a deeper architecture. But if it is shallow architecture, like one hidden layers, you usually need a lot of units. The other question is that we also need to find the appropriate weights. I haven't specified, or we haven't really specified how to choose those weights, but we need to kind of learn them somehow using the data that we have. So that's a part of the machine learning part of it. So far, it was just like representation. What can these functions, neural networks can represent? And also, there are other issues that, well, similar to previous cases, we don't want to learn any functions. We just want to learn functions that generalize well. So we want to avoid overfitting too. And the other thing is that usually we don't want to have too many parameters, but just enough parameters in order to represent our data well enough. So we need to have some form of compact representation. So there are some, of course, details. There's a lot of active research in deep neural network community that studies that when neural networks generalize, what happens if you have, say, for example, more number of units than the number of data points? Do we always overfit or not? And the answer is that no, we don't always overfit. But that's a bit kind of beyond the scope of this course. So I just mentioned them here. Okay, any quick question? Okay, so the next step is that how we should train neural networks using some technique called backpropagation. So backpropagation, maybe a bit of history. I think I mentioned last time that, well, neural networks something like neural networks that we have started from the beginning of what we know as AI. I think, if I'm not mistaken, Marvin Minsky, who is one of the fathers of AI, his thesis or PhD thesis was something that had neural network in it and reinforcement learning. So he did some reinforcement learning with neural network. And there were other neural network-like architectures. But most of those architectures were basically shallow, like they had maybe one hidden unit or no hidden unit. So very shallow architecture, they were not deep. And then Marvin Minsky himself, I can't remember when, I think it was 60s. So he published a book with Poppert, who they basically showed, the book was perceptron, and they showed neural network can be quite limited. So they published that book, and because of that, showing that they can be limited, the result was that the research in neural network stopped for a long time, for I guess more than a decade. So people thought that, well, neural networks are not good, so let's not work with it. And what he actually showed, I haven't read the book, but from what I read about that, is that they showed that neural networks that are shallow, they can't represent things very well. So the XOR example, if you use a very shallow network, they can't represent arbitrary functions. But the issue was that we shouldn't work with very shallow networks. If we go deeper, have multiple layers, the representation power of neural networks becomes much more powerful. But what is the issue? The issue is that people did not know how to train a neural network that was more than one layer. So that was the challenge. The training part of it was a challenge. And it took a while before people figured it out. And it was actually in 80s that Jeff Hinton and others came up with this idea of backpropagation, which basically showed the way that we can train a neural network with multiple layers. Like we are not limited to one layer. And so a bit of detail is that this idea of backpropagation, not the name necessarily, but this idea that I'm going to represent is not necessarily completely new in 80s or wasn't new in 80s. People did in some other fields of mathematics, did some idea like this, but it wasn't just known or well known in the AI community or machine learning community. There's a lot of issue. Probably you have seen it on Twitter or elsewhere that there are a lot of, sometimes occasionally there would be a lot of fights. Who invented backpropagation? So there is a very famous researcher, Jürgen Schmidhuber, who claims that, well, all these things has happened a few decades before, and he has a paper with all sorts of citations. So this is a kind of the sociology of how scientific field works. I don't want to go into detail, but it is mostly known that backpropagation, we figured out how backpropagation works, or most people figured out how it works in 80s, even though similar ideas might be there before that. So train backpropagation, using backpropagation, well, the basic idea is similar to many that we had seen before. We just need to use gradient descent, which you know so far how it is. So gradient descent moves in the opposite direction, in the opposite of the direction of the gradients. And the gradient of what? Gradient of the loss function. So the high level idea is that we compute the loss function or the cost function. We compute the gradient of it with respect to each of the weights of the neural network and just move in the opposite direction. And that leads to decrease in the log cost function. So this is just how we should train them. The issue is that how to compute that gradient. Now, maybe before that, so weight space for multi-layer neural network is essentially we have one coordinate for each weight or bias of the network in all layers. So if you have, say, a network that like X is connected to, say, second layer, third layer, fourth layer, each of them goes with some W1, say W2, W3. Each of these weights, all of them together, define a very depends on the size, possibly large vector space. So we want to compute the weights and updates in the weights happen in that space. So this is conceptual, as I mentioned, it's not very different from what we have seen before. So we just need to compute L. We have a loss function, and then J can be seen as the kind of the cost, the loss over all the training points. And then compute the gradient of it with respect to W's and move in that direction. So we just need to have some quick review of calculus. So we have already been using univariate chain rule. So recall that if we have function of f of x, where x is a function of another variable t, and we want to compute the derivative of f of x of t as with respect to w, it would be derivative of d of f with respect to d of x, or derivative of f with respect to x, and derivative of x with respect to t, right? And yeah, we have seen this before. So we essentially need to do something like this in order to, you can think of f as the loss function that we had at the end of a neural network. And then each of t's, for example, would be, you can think of t as the weights that we have. So we just need to go back propagate these derivatives from the output loss to each of those weights. Okay, so suppose we have univariate logistic least square model. So a model like this, that X is multiplied by W, some bias is added that generates Z, Y is generated by some logistic function, activation function that Z goes through. And then the loss would be Y minus T squared divided by 2. So now we want to compute what are the weights or parameters. One of them is W, the other is B. So we want to compute the derivative of loss with respect to W and B. So the usual way we can compute it is like this. That, okay, so this is the loss. So loss can be written, I just put everything there. So it would be sigma of Wx plus B minus T squared. We want to compute the gradient of loss with respect to W. So it would be gradient of whatever we had before. So it would be, okay, so I'm doing very step by step. So because of, so I can write it as 1/2 of gradient of this quantity. And this quantity, if I compute it, it would be sigma Wx plus B minus T times the gradient of that term. And then let's denote sigma prime as the gradient of that function, of the sigmoid function. So we will have the same function as before. The gradient of it, the gradient of this activation function times the gradient of Wx plus B with respect to X. What is that? The gradient of this term would be just simply X with respect to X, so with respect to W, and then the previous terms are there. If we do the same, you can do as a kind of exercise, do the same computation with respect to bias, and you get a similar result, it's a bit different. So what's that disadvantage of this approach?
Pretty time consuming, probably a lot of layers and alignments.
Yes, exactly. So the answer is that it would be very pretty time consuming if you have many layers. Yes, so this is a kind of complicated process. Like even for this simple function, we had to go through several steps. So you can do it if it is simple like this, but if it becomes complicated, maybe if you have a neural network with 10 layers, you can really do this in this way. So what we want to do is some approach that is a bit more systematic, more algorithmic, in a sense that we can actually let a computer does this calculation for us instead of we do it manually. So let's try to have a more structured way. For the computing of the loss, so again, the model is the same. W times X plus B gives us Z. To activation gives us Y, and this is the loss. Now, what I'm doing is trying to write it a bit more in a clear way, and then go essentially from the last layer or the last step of computation to the first step of computation in a backward fashion. So first, let's compute the gradients of L with respect to Y. So this is actually derivative that I just mentioned, call it gradients. So gradients of L with respect to W would be Y minus T. So this just comes from there. Now I go one step back. So what was the previous step before L? Yeah. Okay, so what was the previous step? It was, we computed with respect to Y. Now we want to compute with respect to Z. So what we should do is that compute the derivative of L with respect to Z. We can write it as a derivative of L with respect to Y, and then derivative of Y with respect to Z. So this is easy because derivative of L with respect to Y we already calculated in the previous step. Now we need to compute the derivative of y with respect to z. So this is through chain rule, but that's easy because derivative of y with respect to z is this sigma prime of z. So you see what is happening here is that I used what I computed, the derivative I computed at the previous step in order to compute the derivative at the current step. So if I have computed derivative of L with respect to y, I can just multiply it by this thing, this term here. And now I can go one step backward. Now I can compute gradient of L with respect to W, weights. So again, the relation of, what is the relation? So it can be, we can write it as gradient of L with respect to Z. This term has already been computed here, times the derivative of Z with respect to W. So derivative of Z with respect to W, so this is Z with respect to W. We see that it's just X. So maybe, so this whole term becomes X, and this other term, gradient derivative of L with respect to Z, has been calculated before. So if I have, in the previous step, I computed it, so I can just plug it back here. And the same for L, derivative of L with respect to B. So here, okay, so here what is important is that first we can compute all the necessary derivatives just by moving backwards from the end in a very systematic way and just compute it. And then in each step, what we need to compute is just the information from the previous step or the next step, I guess it depends which direction you go. So for example, at step Z, we just use information from step that we computed derivative with respect to Y. And then the same thing here. So we just did this computation and everything was easy. Okay. So we can show it in a more kind of nicer way by thinking about computation graph, which basically says that how inputs are, how the output is generated through some multiple steps of computation. So here what we can do is that this function that we have, the loss, can be seen as this computation graph, that Z would be a function of X, W, and B, right? So in some way that is defined here. So that is defined that computation step. And then there would be a computation from Z to Y, so going through this segment. So from this step to this step, there's another step of computation. So here Y does not depend on X directly. It only depends on the information that is already available in Z. And now when we want to compute L, L depends on what? L depends on Y, but also it depends on target T. So Y and target T. So there are two inputs to this one. What we want to compute for training this structure, simple neural network, we want to compute the gradients of L with respect to W and B. So we just need to compute the gradient of this loss function with respect to each of W and B. So the way we do that is just start from the end of it and gradually, step by step, go back in the computation of derivatives until we get to the derivative with respect to quantities, variables that we are interested in. Okay, so we can have now I'm introducing some notation that might be a bit more convenient, but this is not a standard notation. So I use some variable bar, for example, y bar, to denote the derivative of the loss with respect to y. So this denotes derivative of loss with respect to y. So y bar means that. Z bar means derivative of loss with respect to z. So we can do the computation again like before, that derivative of loss with respect to y, which is y bar, is y minus t. Now derivative of z, derivative of loss with respect to z is just y bar derivative of sigma of z. The same for derivative of loss with respect to w is z bar x, and the same for b. So you see that again, as at each step, when I want to compute, when I'm at that step, I just need to have information about the previous steps, or closer to the end of computation graph step, in order to compute my derivative. Okay, is there any questions from this? Yes.
It seems as if you're taking more derivatives in this step as opposed to the traditional. So how are you controlling on, like, how are you speeding up the process?
So I guess the question was that we are doing more computation here compared to the previous case. This gives us, that's true, but this gives a very kind of algorithmic and mechanical way to do the computation. You just step from the end of your computation graph and gradually come back. So that's we do possibly a bit more computation, but the price is that we have a very simple procedure for computing the derivative. And I'm going to talk about it a little bit more, kind of actually give an algorithm, but that's the benefit that we get.
They're not reducing on the computation, they're making it more systematic.
Yes. So the goal is not to reduce the computation necessarily, but to do it systematically. And maybe one thing that I should mention here is that this computation, I lost the screen. So I don't, here the goal is not to find a kind of nice formula for the derivative, but just we want to compute the value of that gradient. So here I'm not plugging all the formulas together, but just plug the value that is computed, say for example the previous or next step in the computation, in order to compute the gradient with respect to this step. So these would be, say for example, when I'm computing here, I want to compute the gradient, or maybe actually I can show it here more clearly. So, for example, when I want to compute the gradients with respect loss with respect to W, I just want a number here because that's what I need. So, in order to do that, X is a value, so 5.1. If I have this value of Z bar, like 3, which is computed through here, that is all I need. I don't plug all the formulas in a symbolic way together. So that's the difference between what we have here and what the kind of the usual standard calculus way of doing things would be, because you keep everything symbolic from the beginning to the end. Okay, so
Excuse me. I had a comment.
just maybe we can have a break. Now let's have a short break, like it's 12 past 12. Let's start at 16, 4 minutes. Ahmad, do you have a question?
Yeah, I just had a comment about the question that was just asked. In these simple cases that we just introduced, yes, it might be the case that we're increasing the computation a little bit, but in more complex situations, when we have layers with multiple units in each of them, and they're very big, by doing it this way and storing them in these partial gradients as we go along, it lets us reuse these gradients, and it actually reduces the computation too. So, I mean, we're getting both the benefit of it being systematic and reducing the computations, because doing the closed form for every single W would mean that we recalculate some of those partial derivatives each time.
Yeah, thank you. Yeah. I guess if it's very complicated, then you can't really simplify the computation of your gradient in the symbolic way. So you actually need to compute a lot of things. In the simple case that we have, we can simplify many things. Okay, so let's continue the break. So we still have a few minutes. Okay, so let's get started. So there's just some comments that some questions that I would like to answer. So one question is that how do we know the target for each hidden layer? Or do we just train all the weights for all layers together? So that, yes, we train all the weights of all layers together. So that's the plan. So there is no specific target for each layer. And another question is that, is there a confidence level associated with the weights of hidden layers? Not really in what I'm describing here. So there's no confidence, so just single weight. If you want to talk about Bayesian neural networks, or you can think about confidence in more complicated ways, but it's not what we talk about. Cool. Okay. So, yes.
I just one quick question. This, like, is that Farahmand, or these would all be evaluated at the current, I guess, operating point?
Evaluated the what? Current?
These would all be evaluated at the current operating point.
Yes. So, yeah, the question is that whether they are evaluated, these gradients, derivatives are evaluated at the current operating point. And the answer is yes. So, for example, we have some specific weights. So you see that, like, when you want to compute, say, any of these quantities, say, for example, y bar, you need to have the value of y. The value of y depends on the input, and also the weights that is multiplied to that input and that went through the whole network in order to give you the y value. So when you want to compute this gradient, get a number out of it, you just use the current value of weights and that x in order to get all this information. Yeah, that's a good point. When we want to perform a gradient descent, these would be actual numbers that are evaluated the current value of inputs and weights. Okay, so another thing is that suppose you have a computation graph that has a fan out larger than 1. So for example, you have this weight here that goes through Z and goes through R. R here is the regularizer. So here this is the case of L2 regularized regression. So input X, Y, L is the same, but at the end we have the L of regularized loss, which has loss plus the regularizer, and the regularizer is that. So you see that there are 2 paths for the weights to affect our loss. One is through this path, the other is through this path. So this makes the fan out of some node in this computation graph to be larger than 1. So what should we do? In order to deal with it, we need to have some kind of multivariate chain. So just another example that I have here is softmax classifier with cross entropy loss, which can be seen computed like this. So let's talk about multivariate chain rule. You all know it. I just briefly mention. Suppose you have a function f of x and y, and each x and y, they are a function of t. So we have x of t and y of t. Now, when I want to compute f, derivative of f with respect to t, I basically need to use the multivariate chain rule, which says that compute derivative of f with respect to x, multiplied by derivative of x with respect to t, plus derivative of f with respect to y, times derivative of y with respect to t. The computation graph that we have is something like this, that t depends on x and y, which each of them depends on t. So there's one path here, there's one path here. And the derivative of t with respect to y can be written as the derivative, these derivatives. And the idea here is, again, as before, we compute the derivative of f with respect to x, and then derivative of x with respect to t. But we do it in a backward way. So this is just an example. So in the context of okay, so I did not mention that. This idea of propagating the derivatives from the end of the computation graph to the beginning is called backpropagation algorithm, or backpropagation. And I'm specifying, I will show the algorithm itself, but basically what I'm describing is the algorithm. So if you have a f, which you can think of it as, for example, your loss function, and you want to compute it, the derivative with respect to t, and you can think of t as sum of the weights, that goes through 2 paths, for example, here, and many things can happen here. But suppose there are only 2 paths here, we just can write it as derivative of f with respect to t would be derivative of f with respect to x times d of x to d of t, and the same for y. And the thing that is important is that if you start from the back and gradually come back, you have already computed, when you are at this stage, you have already computed d of f with respect to d of x. And the same for y. So this is, sorry. So, and the same for y. And in our notation, when we use bar to denote derivative of, say, loss function with respect to that variable, it means that t bar, which would be d of L with respect to d of t, is x bar times d of x dt plus y bar d of y dt. So that's what we do. And since x bar and y bar are already computed, we only need to compute d of x to d of t. So backpropagation algorithm, just write it as a kind of algorithm, would look like this. Suppose we have a computation graph like this, that the input starts from x1 and the output is 7. So not x1, input is node 1, and then we compute node 2, node 3, and then node 4, node 5, depends on node 2, and then so on and so forth until the last unit, node 7, which depends on node 4, 5, 6. We just put them in a topological order of the, let V1 and V2 be in a topological order of the computation graph, which means that parents comes before the children. So just the order of computation should be the way that parents come before the children in the computation. So if we do this thing, we have two stages in this backpropagation algorithm. One is called forward pass, the other is backward pass. Forward pass is just going through the computation graph and compute everything that we need. So for I from 1 to n, we compute v of I as a function of its parents. So for example, I compute, say, 2 as a function of its parents, or 3 as a function of its parent, 7 as a function of its parents, which are 4, 5, and 6. I think there might be an error here in this figure, because this 6 and 5, this is not right, because 5 is computed based on 6, so it should be a bit different number. I think if we replace them, so if you make it 5 and then make this 6, I think it should be correct. So, but this should be, any quantity should be computed based on smaller numbers. Okay, so this is forward pass. We do all the computation. And the backward pass, we start from the end. The derivative of the last node with respect to itself is 1. And then we start from n minus 1 and just gradually go to 1. And for derivative of the output with respect to vi would be summation of derivative of vj, okay, summation over all children of vi of the vj bar times derivative of vj with respect to derivative of vi. Yes?
PA the parent?
That PA is parent, yes. Yeah. Okay, so this is the backpropagation algorithm. This is describing what I described through some examples. And we can think of it, how it is working. For example, in this case, this is a logistic regression model. So forward pass is through this computation. We get to L of regularized to be L plus lambda times regularizer. So derivative of regularizer with respect to itself is 1. So that's the end of it. And then derivative of L regularizer with respect to R would be derivative of L regularized here times d of L regularized with respect to R. So for this, we'll look at this term. And we see that we get derivative of it, we get a lambda. And then the L bar would be L regularized bar times d of L regularized L reg to d of L. And you see that computation of this, there's a constant 1 here. So that would be the same as L reg. And we already computed L reg bar. And now for Y bar, we do the same thing, but we get L bar times Y minus T. And this is coming from d of L to d of Y, which is computed here. And then we can continue the same thing until, for example, we get to computing the derivative of L reg with respect to W. So here, there are two paths, one through Z, one through R. So W bar becomes Z bar times dz to dw plus R bar times dr dw. So Z bar is already computed. dz to dw, okay, so where is it? dz to dw is just x. So that would be the x. And then R bar, we already have it. dr to dw, we computed using here. This is a square of w, so the derivative of it would be just w. And we can do the same for p bar. So this is doing the backpropagation algorithm on this univariate logistic least square regression. And we can do the same thing for this sample of multi-layer perceptron. I suggest you to go through it to see whether it makes sense or not. I mean, it is just doing a forward computation from X to L, and then backward computation of this derivative to get to derivative of all the quantities that we want. So derivative of what we want, derivative with respect to all these weights and biases. And this was for the last layer. These are for the first layer. And these are all we need to perform gradient descent. We can also write this in vectorized form, which would be nicer and more compact. So the results would be just more nicer and more compact. And we can do this. We can also, in the computation, when we implement on computer, because it's using kind of matrix and vector calculations, GPUs would do it much faster than just doing summations. Maybe one thing that I should mention that, so this procedure is much easier to do than computing the gradient using the usual way. And you can write it in a very nice way on a computer. Essentially, each module that you can have, if you know that how its input to output is related, you can compute the d of its output to d of its input, and then you have some terms that depends on the gradient of the layers or units further than that in the computation graph, but those values have already been provided by units afterwards. So you can write a very nice kind of backpropagation algorithm that does this computation. One other thing that I want to mention is that if you want to implement a neural network in modern days, you don't really implement backpropagation algorithm yourself, but you just use one of the packages like PyTorch or TensorFlow or JAX or things like that, that does this computation for you for very complex neural network. And I think one of the reasons that we have a lot of progress in deep neural networks and deep learning is the existence of these software packages that can do much of this computation much easier. Like 20 years ago, you had backpropagation algorithm, but you had to write something in C or C++, and there would be a lot of chance for bugs. But these these software packages are kind of optimized, and they are many people maintain them, so they don't have many bugs, and things would be much easier. Also, we have a tutorial on PyTorch this Thursday, so if you want to know how it works, that would be a good opportunity. The tutorial would follow basically the PyTorch tutorial on their website, so you can also look at their tutorials. Okay, so question is, for forward pass, how to initialize the first W and B, pick randomly, or how to decide on the amount of layers? Is it trial and error? So these are all good questions. So yes, usually, for neural networks, we have this phase of initialization, like when we start, we have to initialize our weights somehow. And they are chosen randomly in some way. There are some heuristics of how to choose them randomly, actually. Like, I mean, there are many different ways to pick weights in a random way, but there are some good heuristics that suggest how to do it. For example, choose it with, draw it from some normal distribution with certain mean, usually 0, and certain variance. And usually variance depends on how many units you have in the next layer. And then you perform gradient descent, or actually you do stochastic gradient descent with mini batches, which I talked about a few lectures ago. The other question is how to decide on the amount of layers. Is it trial and error? Yes, mostly. It is trial and error. You get a sense on what kind of network would possibly be suitable for your problem. So, for example, if you want to solve a simple digit recognition problem, you don't need to have like tens of layers. Probably 2 or 3 layers would be enough. And you get it because many other people have tried similar architectures, and you kind of know with this particular architecture what kind of performance you need to expect. And then much of actually deep learning research, you can think of it as people discovering architectures that are suitable for solving certain tasks. So, for example, there is, if you want to solve this ImageNet, which is a data set of images, many images which are quite large, some architectures work better than others, and much of progress in the past several years has been on, say, what kind of architecture would be suitable. But in general, it will be a trial and error, but you can use past experience of others as an initial point, but you may change it for your specific needs. And again, you should be careful to do, if you want to select the architecture, you can use, okay, so another thing, the architecture, like how many layers, how many units each layer is a hyperparameter of your neural network. So you can choose them, the best value, based on what? Based on your cross-validation, based on your validation error. So not test error, but based on validation error, and not training error either, because of reasons we talked before. Okay, so computation cost is not much. So for computation of forward pass per weight is 1 addition and 1 multiply operation. So essentially, we have a weight, we have to multiply it, and then we add them. So computation cost of backward pass is 2 add multiply operation per weights. So you can see how this is working here, but the exact amounts doesn't really matter. What matters is that the order of computation is the order of number of weights that you have. So another thing is that for multi-layer perceptron, this means that the cost is linear in the number of layers and quadratic in the number of units per weights per layer. Why quadratic? Because if, say, you have 5 by 5, or maybe n inputs and outputs in 1 layer, your W would be n times n, so you have n squared number of weights. So that's the quadratic part of it coming. And then if this is 1 layer, if you make it to a layer with the same size of n, just multiply it by n. Of course, in practice, your n, this is not n, but this would be like n of layer, say, I, this would be n of I plus 1, so they may be a bit different, but this kind of gives the order amount of it. Okay, so backpropagation algorithm is used to train most of the neural networks that people use today. There have been some other algorithms for training neural networks, but they were not as successful for multi-layer networks. And it is used in essentially most neural network implementations and everything. One issue with it is that even though it's practically successful, it is not believed to be biologically plausible. So this is probably is not how brain actually trains itself. There's a lot of research to people trying to find something similar to backpropagation and how showing that brain actually doing it. I don't know what is the state of research right now, but it is very likely that brain doesn't do this compute the chain rule and compute from the end and backpropagates the gradients. So that's a part of the issue. So multi-layer feed-forward neural network and in general neural network address the feature learning problem, but how that feed should come from. Previously, we had to design it ourselves, but now this network, if they learn properly, they learn the proper features. And then the other part of this lecture was that backpropagation was a way, or is a way, to learn the parameters of neural network. So there's, of course, a lot of other things to talk about. I wanted to talk about convolutional networks, which are networks that are designed to be more suitable to work with images. So if the input has a structure of image, not arbitrary input, but has a structure of an image, then there are these networks called convolutional networks that are much more efficient in exploiting the structure of an image. The principles are the same, but the architecture would be a bit different. They use something called convolutional operation. If you have some kind of background in signal processing, you probably had seen a convolutional operation or operator, but it's nothing fancy. But I guess I don't have enough time, but the great thing is that there is a whole course on neural network at U of T, which you can take and you learn about all these things and many others. Okay, any quick question?